This is the oscillator from my previous video, nerds80. It has two crystals, and this is a bipolar amplifier which does not contribute to the noise far from the center frequency. And in this video I will study the flicker noise of this amplifier. It has two amplifier stages. First, two parallel J310, designed to have a suitable input impedance for this crystal. And then a second stage with 6 groups of two parallel J310. And this is for the feedback input. The voltage from one turn goes through this series resonator, which is designed to fine-tune the phase angle, a resistor to limit the current, and two groups of 1N4148 to limit the amplitude, and then an inductor to fine-tune the phase to make this resonator give the correct phase at a reasonably proper tuning where the series impedance is very low. And then this goes to the input to make an oscillator of this amplifier and filter. I have provided the box with proper screening now, connected the outside around the box everywhere from here to here with some copper foil, and also the outside with the inside with copper foil around the edges, and a proper lid with several screws to make a RF tight box. And there is also a thick grounding wire to eliminate 50 Hz currents in the system. I have collected the spectrum for nearly 2 days, and I will print this spectrum on paper to try to get reasonably accurate readings. This is what I have got, and I tried to make a line at the appropriate average of these data points. And obviously around this peak the values will not be correct. This curve should be somewhere here. I don't know exactly where, but I have plotted this data on the same diagram I used in the previous video, and those points that I get now, these ones. So up to here they are in agreement with the blue curve, which was the measurement. I had only 2 points before, but with more time I get 2 more that are still correct. And these are close to that peak due to the zero frequency mixing with the second harmonic. And that is a limitation of the system I have. I have disconnected here, and now I'm feeding the signal through 5.6 PF to this point. That is to evaluate the noise from the second amplifier stage only. And in the first test I have 82 ohms in parallel with the 68 ohms in all the 6 groups. I made a measurement without that resistor and the result didn't change much, but now I have been waiting for quite some time, so I have an accurate reading with this resistor in place. I'm running in the interferometer with 40 decibels of carrier suppression. And this zero frequency, second harmonic peak, is not so big anymore as compared to the true noise spectrum of the amplifier. So probably from 50 Hz to maybe 100 Hz. I cannot trust this result, but I can up to 50 Hz. And I will read these numbers and put them on paper. Now I will look at the amplitude, and Next, amplitude and phase noise. And it's obvious at 10 Hz the phase noise is significantly stronger than the AM noise, but at higher frequencies they are equal all the way. And I think the mechanism here is that the phase through the amplifier is very sensitive to the supply voltage because of the varicap way the drain gate capacitance works. So I think the white trace, that's the flicker noise, but the yellow trace, the phase noise, has a contribution from the noise of the power supply, which is visible up to about 25 Hz or so. Now, this noise is low, so I don't have to worry about it. Here are the data points I found now. They bend off here, probably for the frequency modulation, phase modulation, due to the J-FETs. But this is far below the noise from the crystal, so this is no problem. But above, about here, 20 Hz, this noise starts to be important. And above 50 Hz, it dominates. Now there is another amplifier stage that may be even worse, or rather that is even worse, because that is the line I had with the entire oscillator. Here it bends off towards the flat noise floor. At this point, 3 decibels above the flicker noise, which means that the noise floor and the flicker noise are the same. And that means minus 188 dBc per Hertz. And that is in reasonable agreement with earlier findings. I have removed all the extra 82 ohm resistors for the sources on the J-FETs. And I can see pretty quickly that the noise at 2 kHz here is now 145. And previously it was 146. So I have lost 1 dB on the flat noise floor. At close range, the difference by changing this source resistors is much smaller. At 5 Hz there's no difference at all. At 50 Hz it's almost 1 dB. The source resistors are now 27 ohms, and the mouse here is at minus 150. That's minus 190 dBc per Hertz, because I have still 40 dB carrier suppression. So the wide range is better, and I have also tuned a capacitor, the capacitor on the input, and that makes some more difference than it did before, it seems. With 27 ohms here, I have 16.5 milliamp in each transistor, and that's about the highest current I can have to allow 20 volts to these transistors. The tuning capacitor here seems to be a little bit more sensitive than before, and I have tuned it for the optimum position. And that creates the highest possible impedance on the sources of the transistors, and that reduces the wideband noise. The triangles here are the new values I have seen, and the big difference is at high offsets, where these follow the straight line of flicker noise. So the wideband noise has improved, while the close has degraded a little, about 1 decibel here. Now it is way below the noise when the crystal is connected, so this doesn't hurt. And this is an improvement. Now whether it will survive when I connect the preceding amplifier stage? I don't know. I will find out. I placed a 2-to-1 transformer here. The output is no longer matched, but the voltage, the RF voltage on the drains is now much higher, twice as high. This makes a significant difference. The 50 Hz spur here, it goes up on the high side because of this center problem, but the level here is better than minus 136. And I had minus 135 before, or even minus 134.7 with the new resistor value. The sideband noise, the phase noise of the second amplifier, is now the green dots here, and the straight line with slope 1 is here that fits the points. I can see here, start to see an effect of the wide range noise, but it has to be maybe something like minus 193 or so. Anyway, this noise is well below the blow line, which is the noise when I was running the oscillator as an oscillator. So the question is now, where is the noise when I add the first amplifier stage? I have reconnected the two first JFETs to the group of 12, and now I am injecting the signal to the sources rather than the drains. What I see here is unexpected. The mouse is on the minus 139 line, and here is the 50 Hz peak on minus 139. And before at 50 Hz I had minus 136.4. This is a 3 dB improvement. I had expected the opposite change. And at 1 kHz I now see minus 152. Is this line? Well, it's impractical to look at it this way. It's easier to see like this. So minus 152, that is minus 192 dBc per Hertz, and the flat noise floor has to be significantly below this, because I don't see the bending of the line between all the spurs. I think the explanation is when I feed this high impedance point, it is a 5.6 pF capacitor with a source of 50 ohms. That produces a loss here that gives noise in this amplifier. When I feed into this point, it's a low impedance point, which means that the 50 ohm resistor with the 5 pF capacitor does not produce at all as much noise on a low impedance. That's kind of explanation, I think. It will be interesting to see what happens when I make an oscillator of this again. Here is the phase noise I see when running the unit as an oscillator. And I see 182, minus 182 dBc per Hertz at 1 kHz. This is about 10 decibels above the noise when running the unit as an amplifier without the crystal. And why the noise is higher now, I don't know. There could be several reasons, and I have to try to find out what is behind this. There is a problem in the soundcard. These glitches you can see regularly occurring. In the previous video you can see what happens when they are included in the correlation spectrum. I have added a function in Linrad to switch off accumulation of correlation spectra each time there is an interference of this kind. And you can see here in the baseband, right now I have painted all non-used transforms in white. So the time it takes to collect spectra is quite long, and actually some after each group of white lines are also not included, because I didn't do this very cleverly, because I didn't foresee that these events would occur so frequently. Anyway, there is a possibility that these glitches, sometimes this algorithm of mine fails to eliminate them. That could have an effect on the measurement I'm doing. What I see is not quite right. It is the red curve here, about 1 decibels degraded compared to before. But here there is a significant improvement, and this isn't possible. I think this has to be a contribution from a correlated signal, probably due to that pulse occurring on the DC component. So here is a component that is negative and adds into the correlation spectrum. Then it probably becomes positive again, and maybe very small at larger offsets, because here I get these points. Now this is high above the amplifier noise when I run that in the interferometer. It's the red points down here. So something happens when I connect the crystal and run the unit as an oscillator. Or it could be my test system, which isn't good enough. There could be correlated noise in the sound card, perhaps, or something else that I don't know about yet. Here I am looking at the ordinary spectrum, the correlated spectrum between the two channels. It means composite noise on the lower side and the higher side of the carrier. Now, this is 20 Hertz, and 20 Hertz below the noise level is at 9 on the dB scale, or even, roughly. And on the high side, the noise is 4 decibels higher or so. And then I have this noise at the center frequency. It is correlated between the channels, and it originates in the sound card. And what I see here is probably also originating in the sound card, but going up like that, that shouldn't be the sound card. It's probably something related with the crystal. So it could be the noise from the first filter stage, the amplifying transistor, and that implicates that I should do something to the crystal filter, because it seems to be sharper on the lower frequency side than on the higher frequency side. I have disconnected the feedback cable, so here is the noise when the oscillator is not running. It's just the amplifier noise with the crystal on the input of the first amplifier stage. And I see 21 dB on the low frequency side, and on the high frequency side it's the same. So the asymmetry I have seen is not because of the amplifier being differently noisy on the two sides because of a different output impedance into the first amplifier. I am now injecting a signal on this point through 10 nanofarads from the network analyzer. This crystal is a much higher impedance than the source of the transistor, so the crystal will not affect the frequency response. This way I am looking at the frequency response of this crystal filter, transformer, capacitor, tuning, and I'm looking at the output here. Here is the frequency response of the filter, and the span is 200 Hertz. It shows 0 because it doesn't have enough, but you can see that is the curve I have. And I was looking at asymmetry at 20 Hertz, and we can clearly see the response is stronger on the low side and a little bit weaker on the high side. So the extra noise I see on the high frequency side cannot originate in a signal coming through this filter. Here is what I see with a span of 10 kilohertz. And there's the peak. It was a little bit higher, but there is a notch on the high side. I have added a trimmer capacitor here to feed a signal in the other phase to balance the parallel capacitance of the crystal, and a small capacitor here to avoid the stray capacitance of this long wire to load this transformer, because I want a small tuning capacitor here to have the highest possible bandwidth here. At a frequency span of 200 Hertz, the difference is very small. This is what I have now, and here is what I had before, the old one. New and old. So this one is like that. Now I have set the frequency span to 10 kilohertz, and you can see I have a symmetric curve that goes down to from plus 30 down to minus 25 or so. The asymmetry has not changed. What I see here, this is noise, the green curve, that is correlated between the two channels. And maybe it goes something like that. So there is a contribution here from this correlated noise. And this will look like AM noise plus FM noise on this carrier. So I have a contribution to my measurement from this noise floor, and it will add at frequency spacings above 10 Hertz or so. I have collected phase noise for a long time now, and it's clear that this I see here, these are some artifacts. There has to be an interference that comes with a negative sign in the correlation spectrum real part. And the imaginary part is down here, so this is significant. The level I see is minus 185 dBc per Hertz, significantly higher than what I saw with the amplifier without the crystal in the interferometer. The filter from which I extract the carrier used for the detection of AM and FM is about 15 Hertz wide here. That is in order to be able to go all the way up to 4 kilohertz. I'm using the processing in the time domain, which is rather CPU intensive, and at this high sampling rate, well, modestly high, this computer cannot manage more than what you see I'm doing here. As a result, measurement at close range isn't reliable, This is 20 Hertz, and I see minus 154. That's much more noise than I have seen before. I have made a change, however. I have tuned the frequency of this oscillator under test downwards a bit, so this peak is now a little bit further away from the carrier than before. It's 80 Hertz now, so I should be able to do measurements a little bit higher than I was before, but I have to change processing parameters to go close. I now extract the carrier from a filter that is about half a hertz wide. And I had to slow down the sampling rate, so the maximum offset I can see is now 500 Hertz. And here the level is about minus 180 dBc per Hertz. My UADC4 has failed completely, so now I am using the Delta 44 instead. I have not changed anything on the setup, I just replaced the sound card. And it has to run at 96 kilohertz, so I had to increase the bandwidth. It's now a little bit larger, but it's still below 1 hertz for the baseband filter. So that's narrow enough to evaluate close-range noise. But first I have been looking at the wide-range noise, and for a very long time, you can see 192 hours, 158,000 averages. That becomes 158,000 times 50, because that is the compression on the x-axis. That gives 34.5 dB correlation gain. And the curve here, the red, which is the starting point for the averaging, it's minus 146.5. So the best I can hope for is minus 181. Now, looking here, what I see is minus 181. Well, what I see is not the noise from the oscillator. It's not correlated noise, it's the uncorrelated noise from the two channels of the system. And that is also clear because the red dots, the imaginary part, has the same level as the real part, which isn't always yellow. It also has blue contribution, which means that it randomly turns out to become negative. I can compress by a factor of 2 more, and then I see for 500 Hertz something like minus 182, and still the red dots don't differ much from the yellow ones. So the noise from the oscillator is well below this, probably. And that's consistent with what I am expecting, because the measurement in the interferometer indicated minus, I don't remember, 188 or something. And that's still not really certain, because that's up near the limit of the quality of my interferometer. I look back on the measurement I made with the UADC4. Here I can see 6,571 averages, and the x-axis compression is 200 times 0.005. And that leads to a correlation gain of 30.5 decibels. And this was 37 hours, a factor of 4 roughly compared to before, compared to what I had on the Delta 44. And here is the result I had with the UADC4. The noise was at minus 156.5. Add to that 30.5 for correlation gain. That becomes 186.5. That is down here. And as you can see, the red dots are about here, while the noise I see is at minus 180. So minus 180 is the correlated noise of the UADC4, not the noise of my oscillator. And that's interesting, I think. I have a problem. I don't have the methods to look at these levels yet. The close range noise looks like this. It's very ugly above about 20 Hertz here. So it has to do with something regarding the DC peak. But at very close range, I have good statistics, very good statistics, and I can read accurately what the noise is up to about 10 Hertz. At 1 Hertz, minus 122.6 or so. Half an Hertz, minus 113.5. What I see now are these crosses. It is clearly much worse than before. I have seen these values. So something has happened to my oscillators. I did see this already with the UADC4, but I didn't record the results. Then something happens down here. That could be because of the Delta 44. I'm not sure on that. But I also have seen at 500 Hertz I'm clearly below minus 179. And exactly where, I don't know. The degradation I see here is after I had changed the oscillator to turn the frequency downwards. So something is not good in what I did for the very close range noise. Here I'm using an old computer with a Pentium 4 in it, and I'm using here a soundcard Lynx 2A, which is pretty good, but there are problems. As you can see, the noise isn't flat here, and here the lines are blue, which means that the real part is negative, and the imaginary part has the same size. And as you can see, the separation here is much smaller here. So it is a signal. It's noise of some kind. The computer has failed. It says no input here. And that's after 36 hours. So I'm not going to repeat this. What I have seen anyway is that this signal, I don't think it can come from my oscillator. It is some error in this setup, probably crosstalk between the two channels. And since the crosstalk is frequency dependent, it's much stronger at 400 Hertz as compared to 1 kilohertz. Presumably the crosstalk is in the low frequency section, means after the mixers on the way to the sound card. And maybe the sound card, because I don't think it was like this with the other sound cards on the other computer. Well, after all, I decided to try once more with the Lynx 2 sound card on this Pentium 4 computer. This time I'm using the Microsoft MME drivers. The previous attempt was with the Porti-Audio ASIO drivers for this sound card. It has now stopped after 26 hours at 233,000 averages, but this time it doesn't show no input. So I make an experiment. I take and open another window while looking here. And now it starts again, and it says 303,000 averages in 34 hours. It means it was only the screen update that failed, but the program has been running and it still collects data. Now, collecting more data is not what I'm really interested in, because I already know there is a serious problem in this region. There is a signal that is in antiphase correlated. It can't come from the test, from the unit under test. It's a defect functioning of my evaluation system. But now, since it is running, I can look at the amplitude noise. It looks very similar. I can look at amplitude noise and phase noise at the same time, and they are very similar. And what to draw conclusions from that, I don't know. The whole thing is a little bit magic, and I will try to investigate it better. I can also expand the scale a little bit, like this. And at, let's say, 100 Hertz, it looks like minus 160 dBc per Hertz. But the imaginary part isn't very different from the real part. I'm using the network analyzer as a sweep generator. The sweep width is 2 kHz, and I connect it to channel 1 of my 2-channel receiver, and as you can see, it is fairly accurately 50 ohms, as should be. Here is what I see on the screen. The sweep plus minus 1 kHz, with the image a little bit weaker. And on the S meter, minus 10 on channel 1 and minus 90 on channel 2, regardless of the frequency offset from the center, where the signal is very weak. So there is no crosstalk from channel 1 to channel 2 that could explain anything about the problem I see with a correlated signal between the channels at low frequency offsets. Now I have connected the signal to channel 2 instead, and as you can see, it's the same here. There is no crosstalk. I mean, it's below 80 decibels, and the problem I was seeing was not at all at this range. What you have seen up to now was recorded 1 year ago. I have again a UADC4. This time the prototype I was working with when the design was made. And I have changed it because I had many problems with it. And so there is now a simplified front end with only one amplifier stage in front of the ADC. And here is what I see on the screen after only 2 hours. The signal source is the Wenzel oscillator, and I see the noise floor, the flat, at minus 166. And I can see the noise floor of my AD converter down here when the red dots are, that's the imaginary part, -1, 74, but since only 2 hours and 20 minutes, as you can see here. So this is reasonable. I'm now running in parallel also the delta 44, so I switch to that. And you can see the noise floor is the same, but the noise floor of the sound card is very close. It's the red dots here. And at close range, here is the zero frequency and the second harmonic working together in the delta 44, creates a lot of noise. In the UADC4, it looks like this. It's much better. You can see down here, and I go back to the delta 44. It's a huge difference in the correlated noise, but if you look at the noise spectrum, it's not quite as different. Here is the close range noise with the UADC4, and I can go to the other desktop where I have the delta 44 running at the same signal at the same time with the identical parameters for the Linrad processing. And you can see here, it looks very different when I go to the UADC4. It doesn't mean that the noise from the oscillator is lower here. It means that the negative contribution from the zero frequency comes here, and at this point they cancel, so the noise is almost zero. And this is an artifact. And this negative signal goes and makes a contribution up to about here. As you can see when I switch to the UADC4, which gives a correct result. About here I have the proper reading. And this is 5 Hz, 10 Hz. This is the old UADC4 prototype. I have disconnected 3 of the audio channels and sending the signal only to the first channel. And I have done the same for the delta 44. Here is the UADC4 in correlation mode 1. And I have only one channel connected, as you can see here. The first channel is 1.8 dB from saturation. The other ones are much lower. What is interesting here is the blue trace. That is the correlation between channel 1 plus channel 2 and the other part, the RF channel, that is channel 3 and 4 on the audio side. At zero frequency, means very low frequencies, the distance from here to here is much smaller as compared to at larger separations. It means there is correlated noise at very low frequencies in this UADC4. When I switch for the delta 44, you can see the correlated noise between the channels is much stronger. But if I look at some offset, like here, the level of the correlated signal is down here, and with the UADC4, it is very much the same. Although the uncorrelated noise, the white trace, is much higher on the delta 44 here as compared to the UADC4. Sorry, this is the UADC4 and here is the delta 44. The white track is much higher, and you can see from the color of the waterfall, the delta 44, and the UADC4. So I have a problem at close range on the Delta 44. And I can look here in the baseband graph. Here is the UADC4, and you can see the signal which comes on both sides on the zero, because I only one channel now. There is in the other side this red trace, which is highly undesired. And if I go for the Delta 44 instead, oops, I have that on this frequency. Sorry, I moved it. So I have to go back to the zero frequency to look at the level of the undecided signal here, and with the UADC4 it's roughly the same, but of course the noise floor is much lower here, as you can see. The voltage to the reference inputs of the AD converters in the Delta 44 is arranged as you can see here in the original design. There is a 5-volt regulator and a modest-sized capacitor, 820 ohms, and then the two reference inputs are connected in parallel. And the total capacitance is only 22 microfarads here. So there is a lot of noise at both reference inputs, and I have seen this long ago, so I'm not using the original card, which looks like this. I have stopped the computer and removed the card that I was just using, and it looks like this. So what I have done is like this. The modifications I did long ago are in red here. Simply bigger capacitors, 3300 microfarads here, 470 instead of the 10 microfarads at these positions. And this was enough when using the card in a normal fashion. But now, when I'm looking at the correlation spectra, I need better isolation between the two reference inputs. There are actually 3 capacitors on the 5-volt line, 61, 45 and 25. All of them I had replaced with 470 microfarad, and the 3300, that was on the output of the 5-volt regulator. So this is the card I have been using, as you have seen up to now. I have modified the Delta 44 like this. There are now 2 extra regulators, 78L05 here and here, with a low-pass filter. First the normal decoupling on the regulator, 3 kilo ohms, 470 microfarads, and a ceramic capacitor directly on the AD converters, and here. And now the reference voltages should be truly independent all the way down to DC. And they should be low noise also because of this filtering. And this is what the card looks like now. Here is a close view of one of the AD converters. One of the legs, pin number 4, is lifted from the PCB and soldered onto the small capacitors. The same here. As it turns out, the modification I made on the reference voltages didn't improve at all. I have measured the level of the white track, and that comes in the S-meter graph. And what I see is minus 113.7 in the channel where the signal is, and the noise in the other channel is very similar. It's minus 114.1. So minus 114 for the noise. And then there is 3 decibels, the distance between the white and the green curve. And it means the noise floor is minus 117 dBc per hertz, referenced to the strong signal here. I have signal in 2 places. It is not a normal measurement, but it's a way that I can check whether I make a successful modification or not. Here is the UADC4. It has been running in parallel while I was doing that measurement on the Delta 44. The white curve, the average noise, is at minus 118 dBc per hertz, and to that comes 16 decibels of correlation advantage. This means that the UADC4 at minus 134 is 17 decibels better than the Delta 44 as the cards are right now. This is the UADC4 again. I have placed capacitors on the reference inputs to the ADC, and I can see that the green trace now is a little bit narrower, although the peak is at the same level as before, or very close to that. The white track, the total noise, is at minus 120 for channel 1 and 119 for channel 2. So 120 and then 14.5. That is 134. That's the same as before, but a few hertz above or below, the level is lower. And I can see here there is a much bigger difference than it was before. This is the schematic diagram. There is a low noise 5-volt supply, which is connected here and here, 20 ohms, and the biggest capacitor 100 microfarad. What I have done now is to place 470 microfarads across here to increase the capacitance and make this filtering a little bit further down in frequency. The original frequency were 100 microfarads equals 20 ohms. That was 80 hertz. Adding 470 microfarads, which I have done now, limits that frequency to 14 hertz. And it made the noise, the correlated noise peak a little bit narrower. The biggest capacitors I easily can put into the box is 4,700 microfarads. That should bring down that frequency from 14 to 1.5 hertz. To get an idea, I take a look at the curve at an offset of 14 hertz. So here is the center, and 14 hertz, that is about here. And as you can see, the correlation advantage I have at this frequency is very much bigger than what I have at 1.5 hertz here. So I will add those 4,700 microfarad capacitors to see what happens. Something has gone very wrong. This is a recording from the soundcard test mode in Linrad. And it looks good here. I have 2 signals, one in channel 1 and one in channel 2. But there is a problem. There are glitches occasionally. I have made a 4-channel recording with Audacity, Here I can expand the time scale to look at details of these glitches. Or rather, it is not missing data, it is a voltage jump. And I can see in all 4 channels, it's different in the channels, but the first step here, the second, the third, they have a relation. This one here is half as big as this one. And it's the same down here and here and here. And the important thing is the sine wave continues here. There is no phase jump, so it doesn't fetch data from some other point in time. It's just a DC step. And there is a different frequency on the other channel, and the phase of the sine wave is preserved. And this has to be, I think, something that has gone wrong in the digital part of the ADC. There is a filter that is there in order to remove the DC component, and it seems to me something has gone wrong in the firmware that controls it. This has happened some time long ago, and now it has happened again, and it happens frequently, so the unit is totally useless now, because this is a correlated signal with that. So a correlation gain disappears. Before I thought that this could have been something to do with the power supply, so I made some experiments, and while doing that I damaged the unit, so the unit is stone dead now, and there is no more UADC4 for me to work with. This is an M-track quad, M audio. I have modified it significantly with big capacitors at some locations, and also removed the preamplifiers in order to make this box reasonably useful for sideband noise measurements with correlation. I have been running it for a while, and you can see here at close range, maybe below 20 Hz, it is adequate for measurements on the Wenzel oscillator. That's what I'm doing now. It has been running for 13 hours, so 6 decibels better than this could be reasonable by having a much longer time. Looking at close range, like this, and also like this, I can see at 1 Hertz the noise is at minus 114 dBc per Hertz, and about 20 decibels better than this can be measured at this very close range. So the unit is perfectly okay up to about 10 Hertz or so. While doing the modifications to the box, I made some measurements and screen dumps to show the different stages. This is the first. Here only the preamplifiers are removed and nothing else is changed. I did this several years ago because I needed a slightly lower noise floor that can come from not including the noise, the wideband noise from the preamplifiers. Now, when doing correlation, what is important is the correlated noise between channel 1 and 2 as they correlate to channel 2 and 3. And there are 2 AD converter chips. Channel 1 and 2 is in one IC and 2 and 3 in another IC. I'm sending a signal into channel 1 only, so it comes with equal strength here and here. The problem is the signal here. The white track is the average power without correlation, and the green and yellow is the correlated spectrum, and as you can see it is almost the same level. It's only 1.5 dB below the white track. So the noise between the white noise here is highly correlated between the channels, and that is very undesirable for correlation measurements. The level is minus 114 dB C per hertz of the noise which has this spectrum measured in this width, and it is correlated. This is after the first modification. I have added an RC filter on the analog supply voltage, VA, on the chip, and that is 22 ohms and 470 microfarads. And as you can see, it made a big difference. This separation now is 17 decibels. So the correlated noise has dropped significantly. And all the noise is significantly lower. You can see from the color here, it is bluish, and the previous one was not. The level of this average noise, the white track, is now minus 122.8 dBc per hertz, and the green is 17 dB below that. So decoupling the analog power supply voltage separately and not having them in parallel made a big improvement in reducing the noise, the correlated noise that is, which is the important thing here. The next modification I made was to add 22 microfarads tantalum on the reference voltage output pin of each IC. So this is with the first modification only. And look here, it is now much narrower and we can see some spurs. So the correlated noise has been reduced by this extra capacitance. And this level may be a little lower, and the correlated 18 dB. That is not a big difference, but a little. And it looks like I didn't wait long enough to be able to see where the noise floor is out here. So this is good. Finally, I added two 10,000 microfarad capacitors here and here, in parallel to those 470 microfarad on the analog supply pin, and that didn't make much of a difference, but I allow them to sit here anyway. I will now check my system for problems and errors. First I have connected audio channels 1 and 2, and they are 1.4 and 1.2 decibels from saturation respectively. The carrier is set to show 0 here. If I look at the image frequency here, it comes something like 28 dB below. I can check it like that. 28.7. So this is a good image rejection, and the system is not calibrated. This is what comes automatically. I will look at the noise away. The center is at 7 megahertz because I had asked for 7 megahertz here. That's not visible. The frequency box says 7 megahertz. So I go 20 hertz below that in direction towards the signal and have a look at the noise floor here. Because this is the noise floor about 30 hertz above the signal of interest. And Here comes the noise. Minus 133 dBc per hertz, where the signal is, and minus 134 in the other channel, the two other audio. But what I'm interested in here is to look at the correlation between the two RF channels. Now, with open inputs and 4000 averages, I can say that the noise is below 17 dB, below the noise I measure here, which didn't change, or it didn't change much at least. 134.9, 133.5 a dB or so. And that was probably the noise from the vent cell adding to the noise floor. Anyway, this is open inputs. I have added 50 ohm dummy loads on the 4 inputs, and that caused correlated spurs. And you can see it here also. So something is not quite okay. I had a problem when using the D-sub connector for all the 4 channels here. So I have connected B and C connectors here. But they are connected to this front panel, and it is grounded with only this very thin black wire from here to here. And I will place this thick wire there instead to see if that helps. Like this. The noise floor is still at minus 134.5, but the spurs are gone. And I'm not waiting longer for this, it's only 1400 averages, but I don't think the noise floor has changed. Now that the spurs are gone, it should be the same as with open inputs. This is the 4-channel audio amplifier that I have between the Schottky mixers and the soundcard. The output goes through a ground connection here, and then coaxial cables away to the M-track quad. It's obvious that I have a problem picking up 50 Hz as well as 150 Hz. And of course they are correlated between the channels. But the noise floor didn't change, at least not much. It's still minus 134. And this is the noise close to the center. And at wider separations, I can see from the color of the waterfall up here, it didn't change significantly. So the noise level at the output of this amplifier is very low, and it doesn't degrade the performance of the sound card. Now the noise is fairly low. I have been waiting for a long time now, 60,000 averages, but there are many spurs. So at this frequency, 20 Hz above, the correlation gain is 14 decibels only, but that's because I am on a signal, I think. So if I look here, the noise is a little bit lower, but correlation says 19.7. And maybe I have a 10 Hertz measuring bandwidth, so I get maybe something of the spurs also here. I don't know the origin of all these spurs. The setup I have been using is with dummy loads at the input of this 4-channel amplifier. Then I have put the negative power supply, 6 volts for the quad box, comes from these capacitors, which are fed from a 6 volt power supply fairly far from here. Now I have grounded the negative side on the base plate here, and I have placed a mu metal core on the USB cable to stop 50 Hz currents from flowing on that cable. But I have these all other frequencies. It is not 50 Hz anymore. I have moved the dummy loads here, so there is no amplifier anymore, but the ground loops are still as they were before. This made no difference. Here is what I saw with the amplifier in place, and here with the dummy loads directly on the cables. So the amplifier was not the problem. I have disconnected the wire that was connecting the negative side on this electrolytic capacitors to the ground plane of the rest of the receive system. Now this is significantly better. Some of the spurs are gone, here and here, these ones. They are no longer present. And the general noise floor, like this, is now significantly lower. It's the same number of collected data points here and here, close to the same. And generally it is a better picture. I would have to wait quite some time to see this more clear, but I will make one more change to see whether I can reduce the 50 Hz spurs, because I can see now at 50 Hz here is a peak. It was present here also, but not so easy to see. But the other one, this one, is now significantly lower, so I can see the 50 Hz spur. I will save this new spectrum and make one more modification. I have added a thick wire, 6 square millimeters, the blue one here, and made a bunch of the coaxial cables together with that blue wire up to this ground plane I have, where the connectors are grounded, and still the dummy loads here. Now the spectrum looks a bit cleaner. I can clearly see 50 Hz and 150 Hz, but no more. I can look at the previous measurement here. There was 50 Hz, but this is something and that is something else which is no longer present. And the 150 Hz, but here was something else. So some of the spurs have disappeared, and only the mains frequency is significantly over the noise floor, and this is at 200,000 averages. The unit has been running overnight. I have removed the USB cable with the mu metal core that should protect from common mode currents, and now I'm using just a normal USB cable with nothing on it. The difference is not significant. It is there, but not very large. So I have only looked at 25,000 averages now, and here is the previous measurement with 200,000 averages. And as you can see, now the 50 Hz spur here and 50 Hz here, it is weaker than it was here. But the 150 Hz spur here is stronger. I can see it a little bit on the color scale, and it was not visible here. So some difference has happened, maybe because I routed the cable a little bit differently, if it is picking up a magnetic field. The common mode choke doesn't make a big difference. I have connected a 10 ohm resistor in series with this USB cable that has the common mode choke on it, and I'm sending 50 Hertz into this series connected system, and I'm measuring the voltage across the resistor as well as the USB cable, and that is 460 millivolts. And then across the USB cable only, and it is much lower, about 60 millivolts only. This is what I see, 460 millivolts from here to here, and only 60 millivolts across the inductor. Now the current is phase shifted by 90 degrees here, so the voltage across the resistor is also about 460 millivolts. And that leads to an impedance of the inductor of 1.3 ohms. And that is very low and probably insignificant. It should be 3 times higher at 150 Hertz, and it's still not a significant impedance on the cable. So I will try to make something more powerful. I have made a thicker core. I've gone from 6.5 millimeter to 24 millimeters and put 6 turns on it. The previous one was 4.5 turns. This should increase the common mode impedance by a factor of 10. With the new choke, I don't see the mains related spurs anymore. This is what it looked like with the old one, and I haven't waited long enough to get the really low noise floor, but clearly this distance here is now much smaller here. I have connected the 4-channel audio amplifier again, having dummy loads on the inputs. This didn't make any difference in the noise floor before and now, but I'm interested in whether this amplifier provides some correlated noise between the channels, so I have to wait for quite some time to see where the noise floor comes. And I can already see at wider separations out here the color of the waterfall has not changed, so I can see anything of that. So the amplifier does not add significant amounts of noise, but there could be some noise on the power supply, which is common for all 4 channels. This didn't make any difference in the noise floor before and now, but I'm interested in whether this amplifier provides some correlated noise between the channels, so I have to wait for quite some time to see where the noise floor comes. And I can already see at wider separations out here the color of the waterfall has not changed, so I can see anything of that. So the amplifier does not add significant amounts of noise, but there could be some noise on the power supply, which is common for all 4 channels. This is 470,000 averages. The noise floor, 30 Hz from the carrier towards the center, is still minus 134. It was 134 point something before. The correlation gain is 26 theoretically it should be 28. So maybe there is some noise here, but as you can see, this is not flat, so it means I'm not seeing really the noise floor coming from the signal source, or not even from the sound card. This is just random noise. I haven't waited long enough, and I'm not going to wait any longer. So something like 26 plus 134, that is minus 160. On the other side, of course, it is going to be a little bit lower. Correlation says 27 dB with the same theoretical limit. So, but the noise floor is a little bit lower. I have to wait to see. Here I can see a modulation on the signal. It could be caused by the Wenzel oscillator, something on the supply voltage or something internal in it. The frequency is about 7 Hertz. It could be also modulation in the sound card, in the M-Audio M-Track quad. Something 7 Hertz could make a modulation on the amplitude from the AD converters. Here the noise floor is 4 decibels lower and 1 more decibel here. So about minus 165, 30 Hertz on the other side. And if I go far away, this is 250 Hertz away. I see minus 143. And there is some uncertainty in this. I see 29 dB, and that is more than the theoretical correlation advantage, but I'm looking in a 10 Hertz bandwidth. And I can see when running with higher resolution in the baseband graph here, there are many spurs, but they are not visible here because the resolution is not high enough. And that's because with a higher resolution I get fewer averages. Anyway, this looks good enough. All these spurs will be visible in the normal sideband noise measurements I'm going to do. And I don't know where they come from. Maybe I can find something later on. I have switched to correlation mode 2 in order to measure phase noise and amplitude noise with the current setup. And I have set it for very close range, up to 3.5 Hertz only. And there isn't really any need for correlation with this signal source. It's the Wenzel oscillator, because the noise I see with correlation coincides with the uncorrelated noise. So measurements, this is only 2 hours 49 minutes. I could see noise down to here 1 Hertz minus 122 easily, and half an Hertz minus 114 or maybe 12. And of course with more time I could bring the red dots further down. The red dots are the imaginary part, which represents the orthogonal part, which should be 0. So waiting more, this will go down slowly. With these settings I can do measurements up to about 12 Hertz, up to about here. I have a problem. You may see the dots here and also here. It is 7 Hertz and something comes up now and then. Maybe, I don't know. There is may be a signal, but only in one of the channels. And this measurement is very slow because the bin resolution is far below 1 Hertz, below 0.1 Hertz, far below 0.1 Hertz even. The filter from which I extract the carrier for detection is 0.1 Hertz wide only, and it has a Gaussian window, so it takes far more than 10 seconds for each transform. So this is extreme settings, but it shows a little what can be done. Here there is an interference. Maybe I have knocked on the table too hard. Normally I'm not in the room when doing measurements. Here is the AM noise. It is well below the noise of my test system, so correlation is needed to see it. And I need more time to see where it really is. And I can look at AM noise and phase noise at the same time also. So it is easy to see the difference between AM and phase noise. Now I have contracted the x-axis, and there is phase noise comes up here at about 14 Hertz, and that is coinciding with these dots here. But it doesn't come in the AM noise. So this is an odd phenomenon. I don't know what it might be. I have been collecting sideband noise for 90 hours. The signal source is the Wenzel oscillator, and I'm looking for where the problems are from the correlated noise in the sound card. And I can clearly see here there is an artifact, and the red dots, the imaginary part, goes up like that. So here I have a signal that is giving a negative contribution in the real part that is equally strong as the contribution in the imaginary part. And it seems that this shape isn't quite okay, although out above about 100 Hertz it looks okay. So I can do measurements in the close range up to maybe 20 Hertz, and above about 120. But it is a lot of correlation from here minus 140 to down here minus 162. I'm saving screen dumps at different resolutions for evaluating later on. And here is the amplitude noise. When the x-axis is compressed, it seems I can get a reasonably accurate reading from 150 or maybe 200. Sorry, from about 75, perhaps 80, up to 250. I have a significant distance from the real part and from the noise floor as seen by the imaginary part. But here in this region I have a problem with the correlated noise from the sound card. It was better with the UADC4, but I don't have such a card anymore. I have magnified the compressed image, and I'm using a pixel editor, and I can see now that from here to here, that is 200 Hertz, corresponds to 710 pixels. I have magnified the compressed image, and I'm using a pixel editor, and I can see now that from here to here, that is 200 Hertz, corresponds to 710 pixels. I can see also that 400 pixels is 20 decibels from here to here. And then I can put the mouse at various places on the curve where I think is representative. For example, like here, and press the mouse and read the coordinates 1153 and 255. And this way I can read out carefully what this graph represents. And in the same way I can read out the pixel positions in the a little bit expanded spectrum. This is x-axis times 2. I have made measurements on the Wenzel oscillator before. It's labeled 501 and then 25420. And this is the curve I have obtained. And I don't remember when. It was long ago, and it's documented in one of the nerd videos. I have plotted the data points I have here on this printout from the spectrum I have collected just now after nearly 4 days of collecting sideband noise, phase noise in Linrad. And the points come here. And it doesn't look right. And I think this is long ago, before I discovered a 3 decibel error I'd made. So I have subtracted 12 millimeters, which is 3 decibels on this scale. And then I get these points. And that seems to fit perfectly well. It's obvious that above 30 Hertz, already with this not so perfect oscillator, I have an inaccurate measurement because of negative contributions due to the correlated noise in the sound card. So for better oscillators, I think going above 20 Hertz is going to be a bad idea. And above, let's say 70 Hertz, I don't think I can get any reasonable result with this sound card. It was different when I had the UADC4, but I don't have such a box anymore.